Hi everyone, I'm Matteo Franza and today I'm presenting towards Conversational OLAP, which is the work I did with Enrico Gallinuzzi and Matteo Golforelli from the University of Bologna. Nowadays, smart assistants are in companies' agendas in order to provide data access democratization, meaning that companies want to provide user access to data even with no strong knowledge on programming languages like SQL. So the goal of this paper is actually to create a framework to perform conversational analytical OLAP session. And that is because existing OLAP interfaces actually use point-and-click metaphor to navigate the data and while avoiding SQL. But still, if you want to interact with Smart Assistant, then we need a way to translate natural language into GPSJ queries. So with respect to the state-of-the-art approaches, we provide an end-to-end dialogue-driven framework for analytical OLAP session, which is plug and play, so it has no impact on the existing data warehouse, and which requires no mandatory external knowledge to work. That is the architecture of our framework. So you can see that two phases are involved, the offline phase and the online phase. In the offline phase on the bottom, you can see that is about the population of what is called a knowledge base through a feeding process that can be either automatic or manual. In the automatic feeding process, we have our data warehouse from which we extract the metadata, so attribute or measure that are going to compose the structure of the query, and also the values, for instance, the members of the attribute that actually are going to populate the query. This is the core lexicon that we use in order to support the translation, but that, of course, can be enriched using external open knowledge, such as ontologies like WordNet. Then, of course, the user can manually enrich the knowledge base, but still you want to keep this process as minimal as possible. The line phase is the one responsible instead for the translation of natural language. So we have a natural language query, a spoken natural language query that is translated by the speech to text into raw text. Then we perform the interpretation. So we want to understand what is the structure and the content of the queries. That usually comes with some problem related to ambiguities or inaccuracies. And to handle those, we need to, in the disambiguation module, we need to interact with the users by asking her some question in order to solve all these problems so that in the end we can obtain a query that we can actually parse and translate into SQL, and in the end to execute the SQL and return the data to the user. So you can see that the interpretation actually is split in two submodules, full query and OLAP operators that handle two stages of the dialogue. So the full query is responsible to handle the start of the conversation, where we expect a complete query to be actually described by the user, while the OLAP operator actually describes the conversation step. So it's the dialogue step by the meaning of OLAP operator. In the picture, we have three different colors. So green modules are the ones that are implemented but are outside of the scope of the paper. The blue ones are the ones that are implemented in the paper and that I'm going to describe to you, while the gray ones, so OLAP operator and log, are the ones that we are implementing in our extension. So I will start first of all with the interpretation and the full query module. So the full query module is the one responsible to comprehend the query. Rather than providing all the formal background of the papers that would take too much time for this presentation, I will guide you with an example that is based on the Food Marts cube, which is a cube about the sales of product in a given store acquired by customer in a given date. So at first we start with the natural language query, for instance, medium sales for product New York by the region. And what we do first is that we need to tokenize the queries into a sequence of a single word, and also to get rid of the stop word like the that are meaningless for the query. Then what we do is that we take n-grams of raw text and we try to match these n-grams with similar entities in the knowledge base. So to similar known entities in the knowledge base. And where the similarity is actually based on the Levenstein distance. So for instance, as you can see in the picture, we have the n-gram medium that is matched with average, as the two are synonyms. We have the 2-gram New York that is matched with the entity New York, and the n-gram region, which is matched with both the attribute region and also the member region. So you can see the difference as we use two different types of font. Then we have the set of all the possible matched entities. And what we do is that we want to build mappings, so sequence of matched entities, by creating the combination of these entities. And each entities represent a possible interpretation of what the user has said. So we use the mapping in order to be as the building block of our translation. So the translation is based on grammar, and that has been proved to be effective when we have a narrow lexicon. So for instance, we know that GPSJ queries are usually built with measure clause, group by clause, and selection clauses. So the lexicon is not so wide. So grammar-based translation is an effective solution for this problem. Especially our grammar describe and capture the structure of what we recognize as a query, and being not ambiguous, given a single mapping, then we have a single parse tree. So that is a data structure that represents actually the structure of our query. And this is an example of data structure where we have a mapping that have been fully parsed by our parser, meaning that in the optimal case, we have included all the entities as leaves. So we have a tree that represent actually the structure of the query. Reality is often worse, meaning that in addition to the parse tree, we also have some noisy clauses that actually have been parsed by the parser, but the parser wasn't able actually to attach them to the query. So generally speaking, we have a parse forest, so not a parse tree. And in this case, we have a parse forest as the mapping tries to group by on region, but region is a member and not an attribute, and so we know that we cannot group by on a value, so on a member. Generally speaking, if the mapping is fully parsed, the parse forest and the parse tree are the same, so since now on we're going to refer to the parse forest rather than to the parse tree. We have already seen that the parse forest may have some problematic trees, so what we did in the checking and enhancement step is to define the problem, so the annotation that we need to handle. So here you can see two of them. For instance, we have the resin, that is a selection clause that is unparsed. That would be the same also for group by, but I did not annotate that. And also, as the user asked us the product New York, we know that New York is actually a city, so it's not a member of the attribute product. So what we annotated as part of the tree, so that subtree with an attribute value mismatch annotation. So this concludes the interpretation phase, and at the end of the interpretation, we have an annotated parse forest. So given all this annotation, then we enter the disambiguation phase. So some information actually can be implicitly added to the parse forest. So for instance, user has asked us to the product New York, so we can implicitly infer that she's referring to the comparison operator equal. So she is actually referring to product equal New York. But then we need to ask her some question in order to actually reduce the parse forest to a single parse tree. For instance, for the dangling clause, so from the unparsed clause, we can say, we have noticed that there is a dangling clause, so do you want to add it to the selection clause of the query, or do you just want to drop it? And then for the attribute value mismatch, we can ask, we know that New York is not a valid product, so please choose a product among this one. So in the end, we either add the annotation or we just drop the clause. So we reduce the parse forest into single parse tree, and that is what we are able to transform into SQL code. Note that SQL generation is an automatic phase, so I'm just going to skip it for now. We produce multiple mapping, and multiple mapping ensure robustness. For instance, if the user misspelled in a natural language query region with region, then keeping only the most similar entity would completely miss the mapping, so the interpretation that actually includes group by region, so the correct interpretation of the query. So as the rule of thumb, more mappings, more interpretation, and more robustness. In order to achieve a good experience for the user, of course, we need to select and return only the most promising query. And that is done using an optimistic, pessimistic score function that measures the contribution of each entity to the parsing forest, where the contribution is measured as a similarity between the entity and the textual engram. So optimistic means that if we have annotation in the parse tree, in the parse forest, then this annotation are likely to be solved. And that is because we have comprehended what the user has said to us, so solving the annotation is a minor refinement. While we have the pessimistic part of our score, that in which we believe that unparsed clauses are likely to be dropped, and that is because these parts were actually not comprehended by a framework. So actually there can be some noise that user is not willing to actually add to the query. So as a side note, please also see that as we have a score to rank our parsing forest, we can actually rank our mapping by the score of their parsing forest in order to allow the pruning of parsed mappings. So the evaluation of our set is done by relying on real-world analytic benchmark of queries from SAP that we map to the food mart schema. 75% of the queries are actually valid GPSJ queries. Of these, we manually annotated 110 queries with their correct parse tree. Our automatic fading process extracted one fact, 39 attributes, and 12,500 entities from the data warehouse, and we only added 50 synonyms by hand. Of course, we have some parameters. So, for instance, we matched against the raw text n-grams with size from 1 to 4, and we had to choose how many entities do we want to match. So, do we want to match with each n-grams, and also which is the minimum similarity that we consider. And also to reduce further the number of the mapping, we only consider the mappings that cover at least 70% of the raw text. Of course, we need to define the accuracy. So the accuracy is the tree similarity between the parse tree that is returned by our framework and the correct tree. And so the first two tests shows actually how the size of the vocabulary, so the number of matched entities, actually affect the accuracy. So we varied both the number of synonyms, the number of entities that we match with each n-grams, and also the minimum similarity that we consider. And what we can see in both cases is that the wider the vocabulary we use, so the higher the number of synonyms and the lower similarity we accept, the better the accuracy is. And also we wanted to assess how the similarity change, how the accuracy change if we consider the parse forest with the highest score, so the top one forest, or if we choose the forest with the highest accuracy among the first top 5 forest by score. And we see that there is only a slight increase in that sense, and the accuracies overall ranges between 85 and 90%, which is good. Then we wanted also to assess how the accuracy changes with respect to the disambiguation step. So we took the query, the top one query with respect to the score. We apply all the necessary disambiguation step, and on average, you see that the accuracy increases from 90% to 94, which is actually a state-of-the-art accuracy. So to conclude, so far we have provided an architecture for conversational OLAP session that is automated and portable, meaning that it has no impact on the data warehouse, that is plug and play, meaning that we don't need actually any heavy manual lexicon definition, that is robust, providing several interpretations for a single mapping, and so far we translated natural language into well-formed GPSJ queries. So what's next? Actually, as also I showed you in the architecture, we are working on an extension of this framework in order to support the conversational OLAP session, meaning that at first we need to extend our grammar with dialogue primitives. So that are OLAP operators that we need to use in order to manage and refine the previous parts tree in order to carry on the conversation. Then we need to learn frequent disambiguation in order to minimize the number of questions that we use for the disambiguation process. So we need to minimize the user interaction for a better user experience. We need to define a visual metaphor that support actually the interaction. So for instance, a visual metaphor based on the DFM. And of course, we need to perform some tests in order to verify the effectiveness of our system. So this is the end, and thanks for the attention, and be safe.